Scholar program, Vivian Grom. And she will like show a little bit about what she accomplished last summer. So these are people that stay a little bit longer with the CSDMS facility and work on their thesis chapters in some collaboration fashion. So Vivian's gonna like take the floor first. Hello.
But I mean, where's my presentation? Which is not this, so I might need help. So Lynn did send me a Google Forms. There you go.
And this is a screen. Where is it? Oh, this probably?
Maybe, yeah.
Yeah, there it is.
Yeah, there it is. Yeah. This is my presentation. Yeah.
So we'll just drag it over.
So, but that's not being shared through. This is being shared through Zoom.
Okay, so I can stop my share. Can you show that?
Yes, sure.
Please bear with us.
Okay.
We're doing some dancing around like PowerPoints, like everyone's very used to, and we have like big folders of like Google. But like what the students will be showing is all in their Python notebooks. So there's some magic happened to like get Vivian's PowerPoint up.
I'm sorry. Okay, so perfect. Okay. So my name is Vivian Grom. I'm a PhD candidate at LSU, and I was here last summer as a visiting scholar to develop this part of my dissertation, which is basically quantify spatial and temporal variations and LAM outputs. So in summary, I wanted to develop a module that helped people evaluate their outputs very quickly. So let's say you run a model for thousands of years, and then you have, I don't know, 100 outputs, and you just want to stack them together and see where the differences, like where the contrasts in your results. So that's what I tried to do. Well, no, that's what I did. So in more fancy words, I wanted to do this module to perform quantitative and visual assessment of the similarity and variability between simulations. So you're gonna input the outputs of your landscape evolution models into the module, and then you're gonna get an entropy map and autocorrelation metrics. So the metrics that I use were Shannon entropy, which comes from information theory. So you're gonna have this map highlighting the areas in which your interpretations are, different. And combined with that, I also use the spatial autocorrelation coming from Moranzai and Gary C, which basically it's a number that like each one of your outputs will result in a number that is basically the similarity of neighboring values in your grid. So to make those things more palatable, we have this example. So let's say we have 3 interpretations of the same surface. And if you look at them, you're like, where do we have differences? And a way to assess that more quickly is through an entropy map. So with high values, so in red in that figure, you have the places in which your interpretations are different. And with low values of entropy are the places in which your interpretations have similar values. So that will help you with model validation, uncertainty analysis, and then you can have informed decision making. Oh shit, it was this one. So here we have these 3 time steps. It's just like a schematic way of showing what's going on. So here we have, for example, an erosional process, and we're going to pay attention to the cells A and F. So in A, so actually it's good to kind of explain what's going on. So in lighter colors, we have like higher elevation, and dark colors, it's like lower elevation. So in the cell A, for example, you come from like 10 meters to 8 and then 5. And in F, you have the same, you have like the same value and then an abrupt decrease in the third time step. So if you do just a modular difference, you're going to have the absolute value of change that happened in the cell across the time steps. But if you use the entropy map, you see that there will be like a slight difference because more stuff happened to A than in F, right? You have like a small decrease, instead of like an abrupt decrease, even though the module is basically the same. So to have a better understanding of what's going on, I also included some autocorrelation measurements, which again, it's basically, we will give a number for each output that you input in your module. So in here, what it's basically doing is comparing the, getting the value from the neighboring cells. So if you have more erosion, this number will drift apart from 1 because 1 is like the best autocorrelation measurement. And together with Moran's I also included Gary C, which it follows the same idea, but instead of getting the calculation from the mean, it basically uses the numbers themselves. So, but like the high autocorrelation in this case is actually related to 0. So the numbers will drift apart from 0 with the erosional processes. So then I started messing with the models in very simple, like a very simple model that generated topography and soil depth. So in experiment 1, I did the evolution of the landscape with a steady uplift. And in experiment 2, I did like a positive uplift and a negative uplift. Positive, like trying to mimic something of a cyclic tectonic activity. So these are the results. For experiment 1, we have very similar results for a modular difference and the entropy map. But an advantage of this method is that you can end up comparing things in terms of entropy. So if you're comparing like soil depth or topography or, I don't know, grain size, you can end up comparing everything in terms of entropy instead of having one in meters, another one in, I don't know, other presenting, words just fly away. So in experiment 2, we have a better view of what are the advantages of this method, because again, we're having kind of like uplift, subsidence, uplift, subsidence. So if you sum everything up, you're gonna have, you might mask places in which you have higher contrast, right? So in the modular difference, we have like a very thin kind of zone on the higher differences. But in the entropy map, we see that it's actually pretty wide. So regarding the autocorrelation metrics, we see that like for the steady uplift, the landscape will go towards equilibrium. So the numbers will go towards 1 for Moran's I and towards 0 for Gary C, even though like it's very small numbers. And in experiment 2, we see that it accompanies the cyclicity of what's going on in your landscape evolution models. So basically, my point here is say that this autocorrelation metrics will also give you insights on what your model is doing. So the takeaway points is that these 3 metrics provide quantitative insight into interpreting model outputs, enables the comparison of outputs with varying scales and magnitudes, supports the assessment of spatial structure, helps identify quickly the key divergences among your model outputs, and is applicable to any matrix-based data set, which is quite versatile across disciplines. I did like a little test with DEMs and it worked. So I have the code and a notebook also in my GitHub. So if any of you is interested in using that in your research, come talk to me. I'm also looking for a postdoc in December. So thank you very much for inviting me to talk about this.